What's going on, everybody? This is Mr. Diamond, and we are about to go through the notes over units. This is Unit 6, but it's actually Section 2 about units, which is a little confusing. And these guys right here are all examples of SI units. Some of these you may recognize. You may recognize S for seconds. Most people normally get that one. kg is for kilograms. M is for meters as a length. And then the other ones, usually people are a little bit more iffy on. But by the end of this, hopefully you're feeling good about what all 7 of those are. Before we fully jump into the math that we're going to get to the last part of this section, we need to have a better understanding of what units we're going to be working with. A unit is an agreed upon amount or quantity that is used to compare values for multiple sources consistently. The goal of a unit is to be consistent. When someone in one science or laboratory somewhere in the European areas, and someone in the Asian areas, somewhere in South America, someone in North America, all over the world, we need to make sure that all of their units match up. If someone in South Africa is trying to compare things in one number, but then someone over in Scotland is using another number or unit to describe something, and they don't exactly match up, it can run into problems. So that's the goal of a unit. We use imperial units here in America because we're dumb. I mean, there's other reasons. It's mostly just because we're stubborn, but we really shouldn't be using it. Most of the world uses metric units as opposed to imperial units. But there's also a lot of very not scientific ones. There's a butt load, or a butt, which is 108 gallons of ale or 126 gallons of wine. So if you've ever someone said like, oh, I have like a buttload of homework. Well, I need to be more specific. Does that mean the 108 or the 126 gallons of homework? And this is depending on, I think this is actually based on like how many people you could get drunk was, I think, the original estimate there. 1 morgen is the amount of land one man and an ox can till in the morning hours of a day. So if your property was 5 morgens, that means that it would take a man and an ox 5 mornings to till all of the soil. 1 batman, I think it's actually pronounced Batman, not Batman, but 1 Batman, is a Turkish unit that ranged from about 7 pounds to 16.5 pounds historically. They don't use it anymore, but it's an old unit. A hobbit is a Welsh unit. It's approximately equal to 4 pecks. A peck is about 2 gallons. It's used more commonly in measuring things like fruits and stuff like that. And then finally, a grave. This was actually the proposed base unit for the metric system, which I think is hilarious. Kilograms is actually what we base the metrics unit on. It's like the base thing that we use our masses for. But there was an effort to get the grave to be the unit, which I just think is pretty hilarious. So all of these are units, but they're mostly outdated. And if you want to look into more of this information or get more details about them, don't worry, we're doing a unit project that will involve these things in them that most of you have probably already done, but for my AMI kids, you're probably watching this before we've actually done the project. I will actually say buttload is usually the most common one that people want to do because putting buttload or butts on a piece of paper just sounds funny. That's the only one from this list that I will exclude from that project. You can actually use any of these other ones in the project if you have not yet worked on it. So because they can range through so many values, and even notice not even like they could be describing similar things, but like this one was between 7 and 16 pounds. That's a pretty big deal. That would mean that if it wasn't exactly precise, your weight could vary literally up to twice as much as what it was going to be if you were trying to weigh yourself. And as someone who is currently attempting and mostly succeeding at calorie counting, I can tell you that if I woke up one day and my weight was randomly double because I weighed it from a different scale, I would be very upset. So because they can range, scientists basically said if we want our science to really be useful and to actually be doing something that we could really point to, we need to make sure that when we communicate with each other, we're all in the same units. It doesn't help if someone in Turkey is using batmans, if someone in Europe is using kilograms, and then if someone in America is using pounds. We want to make sure that they line up. So in the 1960s, a group of scientists got together and they officially determined which units we would use in all scientific practices. I usually say, I wasn't invited to that meeting, but this literally was a meeting. It took place in France. It's gone through a couple of minor tweaks. There's been meetings since then, but the system has stayed mostly in the same place. And that is the SI units, or the Système International des Unités. I don't speak French. It's French. If you have take French class, you could probably pronounce that much better than I can. But this is the modern form of the metric system. Technically, the SI units aren't metric units. the metric system has become SI units. They're actually kind of different. It's like the more established and refined version of them. It's a set of base units that we use as the foundation for all scientific measurements. There are 7, and all other scientific units, for the most part, somehow come from these 7 base SI units. So they are length is measured by meters, mass by kilograms, time by seconds. Those people are usually feeling pretty good about, like we talked about. Temperatures are measured in kelvins, which is weird. It's not kevins, it's kelvins. Amount of substances are measured in moles. Electric current is measured in amperes. And luminous intensity or brightness is measured in candelas. So these are the 7 base SI units. Now, for a little bit of a explanation of them, because we couldn't say, oh, well, a meter is it's like a meter. Okay, but what's a meter? It's like close to 3 feet. Okay, but what's a foot? It's like a third of a meter. See, we're running into problems with defining them. So part of the other goal of the SI units, whenever they were formed, was to find a actual method that we could lock down and say, this is a scientific, based in nature, that would be consistent no matter what, to determine what this number is. So for meters, we know that a meter is like 1.094 yards or like 39.37 inches, again, slightly above 3 feet. But the actual definition of a meter is that a meter is the length traveled by light in a vacuum in 1,792,450 of a second, which you may recognize, those of you that are astute, is the speed of light. The speed of light is this number meters per second. So if it's 1 over that number, we're actually using the speed of light backwards to define what a meter is, which means the definition of a meter is based on the speed light travels, which seems really weird considering we use it for a lot simpler things, but we had to base it off of something scientific. This was one of the only ways that we could do it. And these types of numbers, because we're backwards justifying numbers that we've already been using, the numbers can be a little bit odd. So if we go to the next one, kilograms, we often are going to use grams in our calculations. Kilograms are technically the SI unit of mass. It was actually defined by a metal cylinder originally. There was literally a metal cylinder. The definition was like a cylinder made of pure this element that has this dimensions. That used to be what a kilogram is. You can still see it if you go to, I don't remember what the museum is in London, I believe, but you can see the actual original kilogram. But technically, based on a radioactive decay and just the nature of the universe, that was going to be a very slightly inconsistent amount. It was going to change by fractions upon fractions upon fractions of decimals over the hundreds and hundreds and thousands of years. And since we don't want that, we don't want it to be held to a physical artifact. We want it to be something that we can just use scientific constants to determine. We instead said it's the mass determined by a calculation relating to Planck's constant in the speed of light. It's really not worth getting more specific than that, but basically we took the speed of light and we took this value that's called Planck's constant that you'll learn about if you take advanced science classes, and we combined those concepts together to give us a kilogram. A kilogram is about 2.205 pounds. Okay, next is we have seconds. Thankfully, this value is still understand. The second is the SI unit of time. We use that in the imperial system as well. Again, very weird definition. The second is 9,192,631,770 periods of the radiation corresponding to the transition between 2 hyperfine levels of the ground state of cesium-133 atoms. So basically, again, you don't need to know this explanation, but if you have energy levels, think about our SPD and F orbitals. In cesium, if we look at where it's at on the periodic table, it's number 55. It has a 1s, or I guess in this case, it's a 6s orbital electron. That element can bounce up to a slightly higher energy level, and when it does, it's usually going to crash back down very quickly. But that's part of why cesium is not super common and can be less stable than the other ones, is it will actually do that, and that change in process will affect how stable cesium as an atom is. So instead what we do is we say, okay, if it goes up and down, that is a one transition between the 2 levels of the ground state, the low energy level state of cesium. If we do that 9 billion times, that happens in 1 second. That gives you an idea of some of the levels of stuff we deal with when we get really advanced into science, that even just a simple atom of cesium is usually undergoing this crazy vibration of energy at a very, very fast pace. One convenient calculation that it is useful to have memorized when we're in this section is that 1 day is approximately 86,400 seconds. Kelvin temperatures, this one is actually also updated in 2019. It's now derived from the comparison of the Boltzmann constant as to the defined kilogram, meter, and second. So basically, they defined meter, they defined second. We had a new definition of kilogram. That new definition of kilogram combined with another constant allowed us to make a specific calculation to determine what 1 Kelvin exactly is. Kelvin is an absolute scale, which is why it's actually used over Celsius. You'll notice that whenever we write kelvins, kelvins don't have degree signs. That's because the degree is telling you it's not an absolute scale. It's to a certain degree. It's shifted slightly. In the case of Fahrenheit, it's also multiplied or divided, but in Celsius scale, it's just shifted upwards. 1 degree of Celsius temperature is the same as a degree of Kelvin, but with 0 degrees Kelvin is the lowest you can go. You can't have a negative Kelvin, whereas 0 degrees Celsius is the freezing point of water. We can get colder than that. In fact, 0 Kelvin is approximately equal to negative 273 degrees Celsius, which is the same as negative 459, almost 460 degrees Fahrenheit. Now, we've gotten really close to that number. We've gotten like billionths of a degree off of it, but we've never actually reached absolute zero, which means that this absolute zero as our starting point is kind of a hypothesis because we've never reached it. So we don't know for sure that that's the lowest it'll go. Oh, I apologize, everybody. It's been a long week. Okay, so one last thing we're going to talk about, and this will be the only other thing on the worksheet this section. There'll be some notes about SI units you have to answer, but then there's going to be some temperature conversions. But converting between temperatures, we can't just multiply or divide. They came up with some weirder ways. If I don't do it on this next slide, okay, I don't. So I'm going to give you the brief rundown on a very interesting story. So Fahrenheit gets a bad rap. A lot of science teachers, including myself, like to kind of dunk on Fahrenheits because it's just it's so dumb. Celsius at least makes sense because it's kind of taking place around the values that humans are more likely to experience. 0 is freezing, 100 is boiling. That's super convenient. Fahrenheit seems very arbitrary and kind of useless, but there are a couple of reasons it is useful. The first is that it gives you, between 1 and 100, a range of numbers that are pretty much the likely temperatures you are going to experience on planet Earth, which is convenient and is efficient. Number 2, it's also a lot more reasonable to describe things in that when you're talking about temperatures that humans can experience for another reason, not because it's the temperature that the Earth is, but because 1 degree Fahrenheit is about the limit as to how sensitive of a temperature change someone can detect. If you take and you have 2 different cups of water, one is 98 degrees Fahrenheit and the other is 99 degrees Fahrenheit, most people can actually tell them apart. They can actually say which one is warmer. Again, it's not a hard and fast rule, but if you go below Fahrenheit, down to like 0.5 degrees Fahrenheit or something like that, it becomes almost impossible for an average person to tell the temperatures apart. So that's another reason it's useful. Fahrenheit was invented by a guy whose name was Fahrenheit, and he was doing it based on medical practices. I think we may go into more detail about where the origin came from later. If not, I'll pick it back up and I'll make sure I send that out at some point. Celsius also has a really fun fact that I really like talking about, which is that degrees Celsius actually used to go the other direction. The guy who invented Celsius intended for it to go from 0 to 100, where 0 would be boiling and 100 would be freezing. And I can only imagine that when he told his colleagues that, they were like, you mean 100 is boiling and 0 is freezing? You misspoke. And he was like, no, 0 is boiling and 100 is freezing. And they were like, but it would make a lot more sense if you flipped it. That doesn't make a lot of sense. And he was like, nope, that's what I'm gonna do. And they were like, well, you invented it, I guess. This is really convenient, but that seems kind of weird. And so they used Celsius for a little while, and then basically as soon as he died, they flipped the scale back. And they were like, okay, he's gone. 0 is freezing now, and 100 is boiling. We're all in agreement? All in agreement? Okay, cool. Yeah, we know that's not what he wanted, but he's gone now, so you can't argue against it. Which I just think is really funny. That the guy who invented it, the guy who used the correct, or invented the correct degrees that we use for temperature, also got bullied into his entire work being flipped around after he died. It's just very funny to me. Okay, finally, you probably learned about these before, but all of these are technically counted in the metric system, so you can use metric prefixes, even though the SI are a more refined version of it, which means you can add kilo to any of the digits or any of the things we talked about. Kiloseconds, kilometers, kilograms, all of that. Kilo or kilo just means 1,000 of something. So 1,000 grams is a kilogram. Deci means 1/10, centi means 1/100th, milli means 1/1000th. So a millimeter is 1,000th of a meter. It takes 1,000 millimeters to equal 1 meter. We'll talk about these in more detail later, but these are metric conversions hopefully you feel pretty comfortable with. That takes us to how we actually do our conversion calculations, which will be the last section here. No guarantee that that video will be one that I actually have recorded because as I discussed with my AMI kids, time is getting a little bit tough for me, unfortunately. But if you have any questions, please shoot me an email. Otherwise, this is Mr. Diamond signing off, hopefully not for the last time. Have a great rest of your day, everybody.